So we are on lecture 4, and the goal for today is to finish what we started last lecture. We were looking at the BMI differences. What would have been a good opportunity to take a quiz? I missed it. Um, 1 second. So we will finish what we started, and we'll do some more hands-on today. We'll be doing actually 3 different examples, all um, related to what what we're going to discuss either today or what we discussed in the last class. So we started by discussing what is a student's t distribution, and the idea behind student's t distribution is very simple. It's a generalization of Gaussian in some sense, which allows you to capture fatter tails. And the reason we saw this is in the context of a particular use case where it was used first time to model differences or to show statistical significant differences between 2 different kinds of grain being used for in a brewery. What we started to talk about was how to think about a student's t distribution. So if you have x1, xi's to be independent random variables, which are all Gaussian distributed, and you can calculate the sample mean, the sample variance. 1 second. I did not realize this screen is off. What follows t distribution then is this quantity xn bar minus mu sigma square root n by s. And the first handout or the first hands-on that we're going to do today is going to just simulate this, right? So people who have laptops, if you can go to the website and open up the syllabus, you will find links to, sorry, it hasn't been updated, just give me 1 second. Sorry, this should have gotten updated, but just need to run this. Okay, sorry about that. It'll get refreshed in a minute or so. While it comes up, the idea here is what we're going to do today is what I showed you on the previous slide, which is you have these different ways of simulating t distribution. We don't need to do what we are going to do actually, because in general you can actually use any random number generator to generate a t distribution. But the reason we are going to do this is to actually give you a flavor of how to think about what is it doing and how is it doing it. Okay, hopefully this comes up. Takes a while to refresh. Should come up soon. Okay, should be up now. What I am doing is it will, if I click on the first link, it takes me to a raw download link for lecture 4a .qmd. QMD is markdown. Again, I am using R, but you can use whatever language you want, right? All we are doing is literally implementing these equations. So you're not bounded by this language. It's just that I can only do one language at a time. And right now my choice of language is R. So in this first code block, I have written a very simple code block, which I call simulate t distribution. It takes 3 inputs, n, mu, and sd. So n is the number of samples. For example, 1 second. For this example, the number of samples is just this n as to how many number of Gaussians you are summing up. Then comes your sample variance, so that you calculate your sample mean and sample variance. And that's what this particular code block is trying to do here. So the first code block essentially simulates a Gaussian random number variable, a Gaussian random variable, and the way to do any simulate any distribution in R is very, very simple. It starts with an R and followed by the name of that particular function. So R norm means I'm simulating a normal distribution. Okay. The next thing that I do is I calculate the mean, I calculate the sample variance. I'm just using the function in R to do this. And finally, I'm defining my t-stat, which is again just simply implementing this equation. I'm going to pull it up side by side so you can see it. So I'm literally implementing this particular equation here. And since my goal is to actually show you that what does the distribution look like, every time I do this, I'm actually just calculating one number, right? So if I take n Gaussians and if I calculate this quantity, this is a single quantity coming from a Gaussian random variable. So I do it multiple times to show what does the density look like, because I'm making a claim that this follows a t distribution with n minus 1 degrees of freedom. Okay, is that part clear? So from n you collapse to 1, but if you do this 1000 times, 10,000 times, you get the distribution of what does that particular variable distribution looks like. Okay, everyone with me? Any questions? People who have not who don't have laptops, I would strongly recommend you sit next to somebody so that at least you get a flavor. Of course, all of this is available, so you can also go back and try this exercise. Okay, so if this code is clear, here what I'm doing in this particular code block is what I return here is the t values, but I also return the degrees of freedom, and you will see just now why is that. So I can run this, you can click on this particular code block here. It is right now creating a data frame, and it's keeping track of all the data frames one by one. So this particular loop simulates t distribution for a given degrees of freedom. I should have written it as df, but n is basically the degrees of freedom. So for n is the number of input random variables, number of Gaussian random variables that you input. It will output a data frame which will have the degrees of freedom, which is n minus 1, along with the t values that it is simulating. And I'm doing it for three different kind of Gaussians. Just very simple example, 3, 5, and 7. You can of course change these numbers. In this particular code block, what I am doing is I'm just simulating this with different numbers, right? So this is your degrees of freedom, 2, 4, and 6. Once it is simulated, I can just plot their density. In R, it's very, very simple to do. I don't have to calculate the density. I just do geom density. It will draw these density plots for me. In whichever language you have, I'm sure there are ways to do this. Otherwise, I think probably in matplotlib also this is somehow supported. I don't remember, but I'm sure any language, ideally if it is meant for quick visualization, should support these kind of functions. Is this part clear? Right, so we get 2, 4, and 6. You can increase this number and see what happens. Can you actually try to get this curve that I had initially shown, right? Like, so does it look like this or not? You'll have to zoom in and see what differences happen in that particular region. The range, of course, is not constrained here. Then I will hide this. What I'm doing is actually something which can be done in R as well, right? So in R, rather than going through this long route of you describing how that function should be created, I can just similar to what I used for generating normal number variables, R norm, I could have just done RT with the number of data points that it should generate and with the number of degrees of freedom. In this case, this is 2. The comment says it's n equal to 2, but it's basically df is equal to 2. Okay. Here, I am going to now compare my generated version. So the generated version is from R and the simulated version is from the code that I wrote. I want to make sure that the code that I wrote makes sense to some extent. And here I'm plotting them one over the other. Right? So I'm trying to put the two data frames together and see whether they overall make sense or not. And you cannot see the two curves because, well, they overlap, right? Which means that the what R is doing internally using RT is something you can simulate by writing your own function. And this is just an example. If you understand any function, what is the defines what is the mathematical definition of that function, you should be able to implement all of this, right? Like there's nothing very hard about this. Any questions? So very simple exercise just to give you a flavor of. I can teach you T distribution, and tomorrow you'll come across a new distribution. How to think about how will you simulate it? That's what this exercise was for. Right? There's no way I can teach you. We can do this exercise. I can like there are 1,000+ distributions. We can simulate all of them. But if you know how to do this, this is the way to go about. If you know the mathematical definition, it just requires implementing it. Any questions? Okay. We'll continue with the rest of the lecture. Okay, so people who have seen this earlier, what is, you have come across two terms, right? We calculated variance. Square root of the variance is called the standard deviation. There's one more term called the standard error. What is the standard error? And why does it matter? So standard deviation is something that you define for a particular reading that you take, right? So this, for example, if I took x1 to xn, how do I calculate the standard deviation here? These are the different data points that I'm taking. Okay, mu, which is what? Okay, mu or something. So let me clarify some few things, right? So whenever you write mu and sigma square, right? So when I write normal, a normal distribution is often written as mu and sigma square. Hmm. So we'll not go there because last time when I taught this, people were like, this is an introductory course. You should not talk about expectation and variances. So I will not talk about expectation and variances. But the idea here is that essentially what I'm trying to essentially do is I want a measure of how spread the distribution is. Right? That's what the general idea of calculating the standard deviation is. What is standard error? Why is there an error? Standard deviation is just the spread of something. What is standard error? Hmm. So reading, what reading would this be? Like what are you measuring? Right. So you're measuring sample means, right? So both of your answers adds up. Basically, you're essentially measuring certain quantity and you're doing it multiple times. And this goes back to the discussion we had in the previous class that there is a population. So this entire, let's say, world is a population. There's no way you will be able to sequence it, or there's no way you will be able to uh, measure what is going on in the entire sequence, in the entire world. What you do is you take out small samples. You can take out a sample from here, you can take out a sample from here, you can take out a sample from here, and you can, for each of these samples, you can calculate what does the mean look like. Okay, now this mean distribution is, this mean itself, will it be the same across samples? So it's going to differ because, well, the observations have differed, and standard error of the mean is, if I do this experiment multiple times, how much does the sample, how much will this particular mean that I'm calculating, how much will it deviate by? So if you want the standard errors to be very small, what should you do? Large sample size. So which n are we talking about? Are we talking about this n, the sample? So there is an n which is the sample size. and there is a n of the number of samples that I'm taking, the number of times I'm taking the sample. Okay. Number of samples. So number of so each sample size is n. Is that what you mean? Okay. Why should it go down?
No, the n is actually the number of samples. So as we take more and more samples, the error should reduce.
Okay. Anyone has any thoughts? Question is clear, right? So we are in this world where we want to estimate something properly, and you can always take a sample. But for that sample to make sense, we for that mean to be a reliable mean, we want it ideally close to the population mean, right? Where there's no way we are right now, we don't have access to the population mean, but our goal is that if I take this particular sample, how close do I get to my population mean sample, or how much deviation do I see if I take the samples again and again, right? So that's the sample error or the standard error of the mean. So we'll formalize this in a bit. The idea behind, of course, the first part is just the standard is the standard error of the mean, which is x bar is a good estimate of the population mean mu only if you can actually quantify how good is it, right? So if you could sample the entire population, right? So that's an hint to how to think about how to reduce this. If you could sample the entire population, there's no deviation from mu, but you cannot, right? So the standard deviation of the sampling distribution of the mean is given by sigma by root n, where n is the number of sample points, a number of times the sample mean was drawn. So there is a difference between the number of times a particular sample is being drawn and the number of sample points in. So we'll do this example and it will become clear. So stay with me for now. We unfortunately do not have access to this sigma, right? So if we knew the population variance, we could essentially the standard deviation of the sampling distribution. So the when you're drawing out the sample, the standard deviation of this particular sample is a function of of the total variance you have in your population. However, we don't have access. How does it come to sigma square by n? We'll not discuss it in this class, but you can assume that if you are taking out a sample um, of if you're taking out a sample of size n, then the overall deviation that you will see is going to be sigma by root n. Okay. Since we don't have sigma available, we can use its estimate, which is a standard sample standard deviation S, and that standard deviation is what the standard error of the mean is simply S by root n. So we'll see all of this in an exercise and it will become clear. So standard deviation just describes the dispersion of the data, which is what we saw here. Whereas standard error of the mean is a function of how good is your estimate, close enough to the actual population mean. So it's the unreliability of the mean of the sample due to sampling error. So because once you sample, there will be, you are actually losing some certain information, and this quantity quantifies how much is that unreliability coming because of your sampling issue. So this is the point, right? As the sample size increases, sample mean and the standard deviation both approach the population mean. Hopefully this does not require an explanation. This is probably clear that the sample, as you increase the size of the sample, your mean and as well as your deviation that you're going to calculate will both try to approach the sample, the population mean, right? Hopefully that is clear. The standard error tends to decrease as the sample size n increases. Why? Why do you think that happens? That comes back to the question that I already asked. Okay, so if n tends to infinity, the standard error tends to 0. But intuitively, that's of course why is that happening intuitively? That is the
If I take more and more and more samples, if it is possible to take infinite samples, we're actually taking the entire population.
Mhm.
Then if we can measure the statistics of the entire population, it will be almost close to the population statistics.
Okay. So okay, one more. Okay. So is it the number of samples that I'm taking, or is it the size of the sample that matters? So that's where the original confusion also began. Would you want to take more samples of something, or would you want to take a larger sample size?
Larger sample size, but also it depends on how many times I do sample. That can also remove some of the biasness.
So in most cases, you would not be able to do that kind of experiment, right? You would generally take 1 or 2, 3, 4 samples and so on. What you want, so it depends. Like that's where the definition of what is a sample and what is this number of samples and what is the size of the sample is very very important, right? So the one way to think about this is if you took everything close to the population, if you take this entire box, then you would be, if you just calculate the sample, again, this is the sample now. If you calculate the sample variance, this will be equal to the population variance. So this is sample, this is population mean. Similarly, the standard, the sample variance that you will calculate will be equal to the population variance. Okay. So in a sense, this is a function of somehow the sample size, right? Now, if you can think that if I reduce the sample by, let's say, half, if you reduce everything by half, what happens to the sample mean intuitively? Yeah. If you take a half the sample size, what happens to the sample mean as compared to mu? Will it become half?
It will remain the same unbiased estimatory.
So yeah, so that's, we'll not do the proof for that, right? But intuitively you see, right, like in terms of, this is your full population, and let's say I've got going to call it p by 2, your x bar is going to be still close, it's approximately going to be mu, right? It's, the hope is that it stays around. However, this is just one realization of it. It's not going to actually happen in reality. It will deviate. It is not going to be close enough. How much will it deviate is what the standard error quantifies, right? So if I'm plotting now this particular quantity, which is xn bar, how much does it deviate for every new sample that I take? That is what your standard error is trying to quantify. Does that make sense? Yeah.
Now related to this, we have a population.
Hmm.
That is a distribution.
Yes.
Sample means are also becoming something else, and those becomes entirely same.
Yeah, yeah.
They are Gaussian distribution.
So I'll read this derivation last time, and the feedback was this is an introductory course. Why you're doing derivation? But if we want to go there, so let's do it. So if you have a quantity, so if, in this class, the problem is there's no way to avoid notation. So xi, if it follows a normal distribution, I write it like this: normal of mean mu and sigma square. Okay, this is the notation you can think about. Question? Oh, sorry. Yes, yes. So I will not do a very formal version, but I'll just give you a flavor of what is really happening. So x follows Gaussian. Okay, so we'll just call it nu of sigma square. What happens to x1 plus x2 if both of them are normal?
They will follow a normal distribution.
They will follow a normal distribution. And what would the shape look like? Assuming this is the real shape of one of them, what would the shape look like?
The convolution of two Gaussian.
Okay, now you're using convoluted terms. So what does convolution of two Gaussians look like? So intuitively, right? There is of course formula and all that, but intuitively, what do you think will happen to this? Like if let's say the height of this is x, which is this is mu. Intuitively, what do you think x1 plus x2 would look like? Height will be the same for this, or different? Okay, we'll come to the height. What happens to the shape? Will it still be bounded in this, or will it shrink? Will it go higher? Same. Same expand. Mentimeter should have been a good thing. Same expand, shrink.
Minus infinity to plus infinity.
Hmm.
So it's always will be minus infinity to plus infinity.
But the spread, that is correct. But in principle, the density, right? So what is this signifying? Variance, right? What happens intuitively? What do you think would happen to if you sum up two random variables? I'm summing up right now. What happens to the variance? Decrease. Why will it decrease? There's no root n. There's no, I'm just summing on them up. We'll come to the root n part. This is intuition. There's no formula, okay? This is intuition.
So if we have like rad x plus y for two distribution, it should be rad x plus rad y. There's two times of rad covariance of x y.
Okay.
It should be increasing.
Yes. Okay.
Let's say
Yeah.
we take an example of a point on x a one and
Okay. Okay. Yeah.
and we sum up those
Yeah.
2 points.
Hmm.
And we call the random variable sum of these two.
Hmm.
So now it can vary from 0 to 2.
Hmm.
Whereas the first one
Good.
should increase.
Okay. So this is hopefully, it's easier visualized than said, right? It is going to like leak out now from those boundary definitions that you had, right? It's going to, the spread is going to get wider. The mean is a quantity which will not change a lot. It is simply summation. So it is going to shift in this case. So we will add up a normalization factor, and that's one of the things which Aditya was mentioning. So if I take look at this quantity, the mean of course is going to be mu, right? Even if I take half, and what happens to the variance? Does it also now? So with two variables, of course, it was spreading, but the mean was also shifting, right? Which I don't want to draw. What happens to this quantity now? So mean I have stabilized, right? So mean you can of course see that if I'm adding something again here, this is not going to change a lot. This is going to remain constant. What about the spread? About so focus on the formula. Okay, one way to think about this. There's no a very difficult formula here. So this is the formula for your variance, right? For this distribution, I'm asking what does this change by? Like if I do half of this quantity. Yeah. So essentially what happens in this case also, even if you add a normalization factor, the spread that you see will still be larger than the spread that you see in this data. And the one way to think about this is you're adding two Gaussians, but how those two Gaussians are adding, if something was let's say being added from here and for that which was x1, and if this was x2, you have essentially stretched apart things which would otherwise not have stretched apart, right? And you're adding these quantities again and again, so this will end up stretching this. Okay, so in a sense, that's where this idea of sigma square by n, and that's where that factor of sigma square by n actually overall comes apart to be. Um, so in this case, this is sigma square. Um, if it is your xn bar, it becomes sigma square by n. We'll not do a formal proof, but intuitively, hopefully, we'll see that that is the shrinking factor that gets added, or the spreading factor that gets added overall. Okay. Okay. We will it's better to see this. Is the best way to see that particular example is to actually simulate it. So if you again, if I switch back to the second notebook, so there are three here. If I switch to the second notebook, it's easier to get a feeling of what is happening, to see how to make sense of the actual data. So this is 4b.pmd. I'm doing a very simple experiment here. I'll set the seed. You should always set the seed for any random experiment. I'm generating a population. So this is population. I can see what does this population look like. So if I just do histogram, this looks like a normal distribution with a mean of 100 and a standard deviation of 10, which means variance of 100 as well. Okay. I define a new function for quantifying what is standard error. Okay. And then here I am drawing sample sizes. Sample size is of 50, and I'm doing this experiment 1,000 times. In this particular code block, I am just sampling from population. I'm sampling, for example, 50 items from this entire population that I have. I'm calculating its mean, I'm calculating its variance, and I'm calculating the standard error of the mean. And finally, I'm just storing all of this, right? So I'm just going to run this particular code block. Okay, now first thing that I'm plotting here is simply the sample mean, right? So the red line here shows you what do you get, what is your population mean, which is 100 that I began with. And this spread that you're seeing is because I drew 50 samples only, but I drew them multiple times. Okay, this is the spread that you get going from 95 to 104ish overall, and that is what essentially we are trying to quantify. Does that make sense? So I took the same sample size, but I took it multiple times. The standard error of the mean here is the spread that you're seeing, that you get from this particular quantity, which is your population mean, right? So this is a measure of how much that population, that sample mean is changing for every particular iteration. Everyone with me? We will also, we can also plot the standard variation, or the standard uh, the sample variance. This doesn't of course have a very high meaning, but we'll see an example in just a bit about what to do with it, right? So you can see this is the 100, which is what we had initially. This is the sample this is the population variance that we had began with. And this is plotting how much does the sample variance of the sample that you're drawing, what does that look like, right? So it's, if you compare this, this is 100 to 160, so around 60 points variation. If you compare this to the sample mean, while the distribution overall looks much similar, this spread here in the case of mean is much tighter, which essentially is the central point there is to show that it's much easier to estimate the mean, because the moment you start to talk about estimating the variance, that's a much harder problem. So with mean, we are able to capture properly, very nicely. But if I want to capture the same thing with sample variance, the spread is going to be much larger. Okay. Okay. Now let's do a different example, maybe just below this. I will repeat this particular study for a different sample size, and let's see what that result looks like. So instead of 50, I am going to now increase the size of the sample to 100. So what do you think should happen? That distribution that you were seeing earlier, this is deviation is standard error of the mean. What happens to, will it shrink? Will it go more wider, or will it remain as it is if I increase my sample size? It will shrink. Why? Okay. So let's do that example. Okay. So it's very hard to see here in terms of what is really happening. But if you were to quantify this, so this is 98 to 102, which is kind of similar to what happens in the case of here of the previous example, but is definitely changed to some extent. Let me make it 500. Okay. Does everyone see what happens now? So these quantity, while the shape has remained of course the same, this quantity is now much closer to that particular number, right? So, and as few, again now just make it 750, the mean will get closer to your actual, actual distribution. 99.5 to 100, very, very close. So that's why in most settings, the idea is if you want your mean to reflect the population mean, you want large sample size. So in clinical trials, in any sort of surveys, the idea behind doing a large sample size is to be able to get the properties of any mean quantity that you're calculating. Most of the time, you'll be interested in calculating the mean and the variance quantities of your sample. This size of the sample that you're drawing helps you shrink down the estimate close enough to what it looks like in the population. So that if you take a large enough sample size and you repeat that study again and again, you will very likely arrive at the population mean, which is what this experiment also shows. Everyone understands what we're doing? Any question? Anything that was not clear? Okay. The bottom exercise is to actually tell you that while we can get the population estimate, let's repeat it actually. You'll see what it looks like. So sample variance, right, hasn't, it was from, if you remember, it was going from 100 to 160. While it has shrunken, it is still a large range. Right? It's still of the order of 10 to 15 points. And the point to show here is while we can capture the sample mean to be very close enough to be the population mean, the sample variance capturing that is a harder problem. You will still have calculating that sigma square or getting close to that sigma square is going to be very, very difficult unless you capture the entire population to begin with. Okay. Okay, all right. So if that is clear, we can move on. So the simplest thing that we want to do, why are we doing all this, right? We want to do all this because we wanted to compare whether the differences between the men and the women BMI is it different or not. And the simplest way you could have thought about this is if I gave you so I could have given you a very simple hypothesis that the mean BMI of males is mu males. So in a one sample setting, I'm interested in identifying whether this distribution that you gave me is this true. This is something which is given. So you would have taken the data, you would plot it, and you would quantify how different are my observations from this distribution or from this given quantity by calculating what's called a z-score, right? So the z-score is simply your value that you're getting. If somebody gave you that this is the simplest hypothesis that you want to test, that whether the BMI of all males is 25, I will substitute that particular 25 value. I'll calculate the standard error, which is sigma by root n, and then just look this particular quantity up on my z-score table. And if this z happens to be in this boundaries, then I will say I reject the null that the BMI is equal to a given quantity. This is what's called a simplest z test, where you're given a particular quantity where the observation follows a normal distribution, and you are essentially interested in testing whether the mean is equal to a given quantity. In this case, that mean being mu naught. But in reality, very few times would you have to ever do a z test, for two reasons. One is nobody actually knows the actual value, so nobody will, it's very hard to find out what the real value is. And second, in most cases this normality assumption will start to fail, right? So we'll see how to test for normality. But this is the simplest test that people usually do if you have a very specific hypothesis for one sample only. But what we are interested in two sample tests. So we have a sample coming from males, we have a sample coming from females, and we are interested in whether there is statistical significant difference between those two samples. So one way to do this would have been to collapse the women BMI to a simple number, and let's say call it mu females, and test this, right? I could have still applied, I could have said that mu males is equal to mu females is my null hypothesis. I can apply a z test here. I can just substitute the values that I get from my sample. This is not mu females, actually this is going to be my x bar females, which is the sample mean, and substitute here in form of mu naught. While this is not fully incorrect, the problem with doing that kind of testing is you're not actually utilizing the power of the distribution that these two quantities both follow. A, this is not the population mean, and B, you know what the sample distribution of the females look like. So to capture that, you do what's called a two sample testing, and we will focus on what's called the unpaired design. The unpaired design is very simple to understand. If you're doing a repeated observation on the same individual, then it's a paired design, right? So if I today, for example, if I measure my blood glucose levels before and after a meal, and if the hypothesis that I'm interested in is that a carb rich meal spikes up my blood glucose, and if I'm doing it on all this class students before and after a meal, they become part of a paired study. However, if I change the design, if I gave a drug to all of you, if I gave metformin to all of you, and in the second class I did not give them metformin and did the same study, my question would have changed, that does the drug lead to a difference in the blood glucose level post and pre meal? You would go give the next class a placebo, so you'll give them a random drug, and you'll give them yourself in this class will give metformin. So in this case, since there is no relationship between the experiments, this is a separate experiment, the other class experiment is separate experiment, they are unpaired. Okay? There is no pairing happening, so we'll do an unpaired test in that case. So for this class, we're going to focus on unpaired tests, but that is how you think about a paired testing. We'll talk about the paired example. Does that idea make sense? Okay. So how do you think about tests? The idea behind thinking about tests, what we are interested in is we are given two distributions. We are interested in understanding whether their mean population, the mean of this sample is equal to the mean of this other sample. There are two ways to think about this. So this paired and unpaired I already talked about. If it is paired, you can do a parametric test. So the parametric test is paired t-test. We'll see this. You can also do a non-parametric test. So what is a parametric test? In parametric test, you know you have certain assumptions about the distribution properties of the data. So for example, in this case, I'm going to assume that these observations are normally distributed, so I can run a particular kind of test. The power, why do you want to make assumptions? Because with assumptions, you get what's called power, and you've seen what is power, right? So if the null hypothesis is actually true, you have the ability to detect what that null hypothesis is. right? So you are able to, it's the other way around actually, not this shaded portion. So you are able to detect if there is actually a change, can you actually pick it up or not? And if you make certain assumptions about your data, you are indeed able to do that. That's why parametric tests are often preferred if you can satisfy their assumptions. Non-parametric tests, on the other hand, have absolutely no assumptions. They don't assume anything about the data except few very small things. And for that, we can either, if it is a paired setting, we do a Wilcoxon signed rank test. If it is a non-paired setting, we do a Mann-Whitney U test. We'll see the example of Mann-Whitney in just a bit. Based on the unpaired set, if the variance is equal, you do something called, if the variance is not equal, you do something called the Welch test, and otherwise you do a student t-test. They're actually all just categories of t-tests. So you can just do t-test broadly. We'll see example in just a bit. Okay, so this is a question we were asking, and we will today in this class see what is the question, that how do we answer this, right? So the null hypothesis we have already discussed is the mean BMI is equal between the male, or is the same for men and women. So before we start to talk about visualizing, or before we start to talk about statistical testing, right, one thing you should always do if you're given such kind of questions is to just visualize it. Leave the statistics aside and try to visualize what does the data look like. So for example, this is an example of a box plot where I'm just plotting the distribution of one quantity on the y-axis. This is the numerical quantity. On the x-axis are the labels. So I should have probably put a better example, but this could be the BMI of the overall BMI. This could be male and this could be female, right? So box plot, there are few quantities that it is measuring. This quantity here shows the median, and these two quantities shows the interquartile range. We'll see the example specifically in a bit. Anything which is beyond the 3 times the interquartile range becomes outlier. So for example, this dot that you're seeing here does not follow the rest of the distribution. So that's why it's called an outlier. Hopefully you have seen one version or the other version of this in your in coming up with data. What the box plot unfortunately hides, it hides the distribution, right? So all the numbers are being collapsed into these numbers Q3, Q2 and Q1. However, we know for a fact that even though the median or the Q2 could look like here, the distribution itself could be different. Maybe most of the data points are indeed uh, distributed around this point, or it could be a very long line where the data set is very, in some sense, uniformly distributed, but there is some more mass here. So violin plot shows you the distribution of the points itself, right? So the fatter it is here means there is more density of points in this area. In other words, you're plotting the density itself on the y-axis along with showing some statistical properties. But there is something which is missing here, right? Like, what is wrong with violin plot? So this is called a violin plot because it looks like a violin. This is called a box plot, well, because it has boxes. Which one do you prefer and why? Or if you don't prefer any one of those? You've all seen some version of this or the other, right? Box plot, I'm sure most people have seen. In violin plot, okay? Yeah, so it's hard, right? Like violin plot by itself is not doing justice. Any changes you would like to? That's right, it's hard to detect outliers. So there is a plus of this, right? You can see the distribution of the data clearly. You can see the properties of the data clearly. There is a plus of this, that you can see the distribution of this data set clearly. How do you match both of them? Or how do you think about matching the pros of both of them? Any ideas? I want to see the distribution and I also want to see the properties of the distribution. Simple engineering fix. Overlap. Exactly. Right. You can overlap, right? So this is just a box plot plus violin plot. It shows you everything. It shows you what is the outlier, right, which is otherwise being masked by the violin plot. It shows you how the distribution of the data set is. So this is a good visual representation. You can just from seeing, right, you know that what is going on. You don't have to do any well, you have to do statistical tests at some point, but this is very contrastingly clear. What is one level of information that you think this is hiding? Is there something that is still missing from here? Anything that you would like to see? Hmm? Right, sample size, right? So there is, I can have a distribution which looks like this and look like this. This could be 100 points, this could be 1000 points. It doesn't do justice to be able to show that. So there are other variations of these different plots. You have the notebook where you can draw all of these plots in just a bit. But ridgeline plot is a different version or an inverted version of iron plot where you can indeed add whatever quantities you want. And then there is something called the bee swarm plot. This bee swarm plot actually shows you the data points as well, right? So again, it only shows you, it's a violin, and it shows you how many number of points there are, right? So for example, there are like what, 8-10 points here. So I can see that this sample size and this sample size, maybe this sample size is overall smaller, right? It's still not very fully intuitive. And one way to make it more intuitive is you can of course mention the sample size here if you really wanted to, but it at least gives you a visual indication of how many number of data points you have. It doesn't show you any other properties. So if you want, you can again bridge the best of the two worlds. You can bring the violin, you can mark the median if you want, and you can show all the properties at once. It's a very good visual metric to show what is going on with your data. Okay. Okay. So in most cases, you would have seen box plots, and we'll just discuss box plot very quickly. So box plot marks out few different regions. This particular quantile, this particular box is the Q1. This is Q3. What is Q1? So Q1 is essentially, what is Q1 actually? Anyone from audience? What is Q1? Q1 is the quartile, the first quartile. Q2 is the second quartile. Q3 is the third quartile, and so on. What is QX or Q? Correct. So Q1 is 25% of the data. So if you calculate a quantity Q1, 25% of your data is going to be below this. Okay. Q3 means 75% of it is going to be below. This is Q2, which is 50% of your data is going to be below. And of course, Q4 is just 100%. Okay. So here, this is Q1, this is Q2, this is Q3. The difference between Q3 and Q1 is called the interquartile range, which basically means that 25% of the data is here, 75% of the data is here, 50% of the data is encompassed in your interquartile range. Okay. And then these boxes or these whiskers that you see, this is Q1 minus 1.5 IQR, Q3 plus 1.5 IQR. Why is it 1.5? Anyone? You have all seen one version or the other version of this, right? Anything which is beyond this will be called an outlier. So for example, here there is an outlier because this does not follow in any of this ranges, right? That's why it's an outlier. Why? What is the assumption that this box plot is often made on? And why is that 1.5? What is so special about 1.5? Why not 1.6? Why not 1.2? Why not 2? Okay, significance level of what?
The threshold value, as we used to decide like for the p value, we used to decide the threshold value. So it's related to that.
So that is partially correct, yes. But why 1.5? That's partially correct.
The standard error
Of?
the Q's like QX we can say.
Okay. It's not quite there, but okay, good attempt. Anyone else? Why would have somebody thought about a box plot? Like what was the assumption? Why is that 50% so important? Can you think about a distribution that would fit? We haven't discussed this in the class, so I'm going one step ahead, but can you think of some distribution which would capture this. We have discussed the distribution, but we have not discussed the nitty-gritties of it. Okay. Okay, what distribution looks like that? Okay, so Gaussian, right? So this is Q2, Q1, Q3. Okay, so this, okay, 50% will be somewhere here. And then your whiskers come in. And this whiskers essentially capture overall, I think that number is 99.7%. Again, slightly historical thing about how it came about to be. We don't have to go there. But if you plot this on a Gaussian curve, this of course captures your 50% data, and then this quantity 1.5 times IQR captures your 24.65. Right. So if you add this up, I think it becomes 99.7. Can somebody check? Or 99.3, not 99.7. Yes. So 0.7% of this data is going to be outlier. The rest of the stuff is captured in here. Okay. And here, the other way, which are more famous numbers here, is how much mass is there between one standard deviation of your mean. So between one standard deviation of your mean, you have 68.27%, and the remaining between one standard deviation and three standard deviation is another 15%, right? So that 90 will if we have time, we'll talk about confidence intervals, and some of these numbers are important there. But this is how the box plot was basically thought about to be, essentially. Okay, clear? Okay, we'll switch to the actually doing the t-test, right? So the t-test here is a simple hypothesis that we're testing is mu1 equal to mu2. We define, just like any hypothesis testing paradigm, we have defined the null. We are going to make some statistical assumptions about the model, and finally we'll define a test statistic. So let's define the test statistic first. This is just y1 bar minus y2 bar, sample mean of y1 and y2 divided by the standard error of y1 minus y2 bar, okay, which has a particular degrees of freedom. You of course know the formula for standard error, which is not hard to calculate. I will give you the formulas in the exam if they are required. All I want you to is just pay attention to the intuition that is. So very complicated formula for the degrees of freedom, so don't worry about it. But essentially what it is trying to capture is it's the sum of the two standard errors of your two populations divided by the total number of data points that are there. Okay, so how does it come about to be? You don't have to worry about right now. But this quantity follows a t distribution with degrees of freedom given by this number. And the assumption that we are making in the case of doing a t-test. So I've described the rest of the recipe, but I have not told you what are the assumptions that we are making in this data. With a very two simple assumptions, and in your assignment you will do an exercise where you'll relax these assumptions one by one. First is observations from both groups are approximately normally distributed, and this approx is the key word. We'll see an example of what that approx means. And the difference of means is independent of the standard error of the difference. In most cases that you will come across, this assumption will hold true, is that the difference that you're seeing, right, the difference between the population means is independent of the variance, which usually holds up in any Gaussian distribution, right? So mu is an independent parameter as compared to this spread. There is no dependence. That is essentially what it is trying to quantify, except that it is trying to quantify in terms of the difference of this quantity. These two assumptions are clear. Approximately normal and the differences are independent of the standard error, which is basically your variance. These two parameters that you assume for Gaussian are independent. We will not have time to discuss some of the cases, maybe in the next class, where this assumption actually for certain distributions is not true. So that's where it will start to fail. So in one sample setting, you can actually also apply t-test in a one sample setting, which is very similar to applying a z-test, except that z-test is going to be very stringent. However, we know and we proved and we saw that this particular quantity follows a t distribution and not a z distribution. So if somebody gave you that the mean of the sample, the pre-specified value, which is that mu0 is the sample mean followed by your BMI, you can do a t-test, a one sample t-test by calculating the mean of the sample, subtracting the pre-specified value mu0 and dividing it by standard error of the sample, which is s by root n, and this gives you t statistic, which again has degrees of freedom. You can calculate what the p value would look like. But in most cases, you will not have this pre-specified value. In most cases, you will apply what's called the two sample t-test, right? So the two sample t-test is what we are dealing with right now. And we're asking a very simple question, which is the given two independent samples, is their mean equal or not, right? We define the same quantity which we talked about, which is y1 bar minus y2 bar, and here we're going to make assumption that the variance of the two samples are different. We took two different independent samples, but their variance, we are already assuming by the null that their mean is equal. There is no assumption about their variance, and that has impact on how the test is done. So in most cases, when you don't know, you take the most stringent assumption is that the variance is not equal. This is also a t-test. It's given a special name, which is called the Welch t-test. Okay. Okay. So this is too much, right? Like this is so much going on. You don't have to worry about all the formula, but intuitively, what I want you to remember is for a two sample setting, you essentially test if this quantity, which is supposed to follow a t distribution, the t statistic that you calculate from this sample, how different, or again, where does it lie? Does it lie here? Does it lie in the extremities? Does it lie here? Okay. Now, when you are doing this, the other thing that you have to do is, of course, also define your alternate. In this case, the simple alternate I defined is they're not equal. But if it is direction, if it has a direction, you need to make your call accordingly, right? So if it is right, that means that you're saying that one mean is greater than two, then you will take this quantity, and if it is one less than two, you will take this direction. Okay, so you have to also make sure you focus on what is your standard, what is your alternate. Okay, how do you test for normality? There's an assumption of test for normality. So for testing for normality, we draw what's called a QQ plot or a quantile plot. On the x-axis, you're plotting theoretical quantiles. What are these theoretical quantiles? Is assuming this follows a standard normal distribution, you have the values for the standard normal basically plotted here, right? So standard normal means zero mean, and usually will go from minus 0 to plus 4 and minus 4, right? This is what the entire spread will die down. Of course, it goes to infinity, but it basically starts to die down about after 4, which is what you're plotting on the x. And then you take the quantity of interest. So for example, I take the BMI of the men and I plot their quantiles. Okay, so in R there is a function where which you can take any data and you can calculate what is the corresponding quantile for that data, right? So in this case, for example, if I see here 1, this is the theoretical quantile, and the corresponding value for the quantile of my data which I am observing is around 22.5 or something like that, right? If these are normal, if this is normally distributed, then they should lie along a line. Why? Why should that happen? My claim is if the rural BMI population is normally distributed, then this should look like a flat line. Why? Say that again. So close enough, right? So essentially what I'm saying is, if this is your standard normal, which defines the shape of the normal, and you take any of your data, right? Take any of your data, its mean could be slightly different. But if there is a correspondence between, so if let's say this is your first quantile, right? I'm just going to call it 1. What is that corresponding number here? So I get that, okay, this is your first quantile. I calculate the second quantile here. I get this number. I calculate the third quantile here and I get this number. And basically what it is saying is this correspondence that you're going to get, if they are both normally distributed, should be parallel lines. And that's why when you plot them on the xy axis, 1, 0 and -1, 0 and 1, and if I plot these numbers, they are also going to be increasing in that order. It's intuitive, right? We'll not do the formal proof, but this is, does it make sense overall? So if things are normally distributed, then theoretical quantile calculated using standard normal as the base assumption, and sample quantile should follow, look like a flat curve. Fair enough? You see that here in this case, it's not happening, right? And that's why this assumption of standard normality, the approximately normal, is very hand wavy. Unless you see like huge deviation, it's okay to run it in cases like this also. And in your assignment, you'll relax these assumptions and see what happens. But any ideas if you what will happen intuitively if this is not going to be true? If the assumption does not hold, what impact will it have on your final test? Will you get more significance? Will you get less significance? Will it remain the same? So you don't have to answer now. We'll do it in the exercise. But let's run this. We have 15 minutes. We should be able to finish this exercise. So what again I will go back to is I'm going to go to the website and finally open the third notebook here. So this first part of the package, of course, just does some installation. You should run it once. We start with a visualization example, which is very rudimentary, but this is a good way to learn R. Like I'm just plotting scatter plot of a different data set, not related data set. This is iris. Iris, of course, people who have worked with this would know it's a data set of plants and coming from different varieties of plants. On the x-axis, I'm plotting the sepal length, and on y-axis, I'm plotting the sepal width. This is totally different. This is just to show you how to do visualization. Box plot, this is what I showed you. This is the same plot that I put in the presentation. 3 different categories of flowers or plants, actually flowers, and flowering plants, and on the length is the length of the sepal. Okay. Violin, again, way to draw this in R is very simple. What do you do, right? So in R, you take the data frame, you specify what is the x-axis, what is the y-axis, and what kind of plot do you want, right? So very simple. This is called the statistics, the grammar of statistics. Like ggplot came out of that philosophy, which treats everything as a different layer, right? So if I wanted to add another box plot, I can just do a plus. It's like literally doing mathematics with the plot. So you can add a violin plot overall, and if you want to do a ridge line, which is this kind of plot, it's like a violin, but you're able to show different quantities. I'm only showing the second quantile, but you can also show quantile 1, quantile 3, and so on. And it also shows you the distribution of the data. You can also do B-swarm plots, which is also what I showed in the presentation. And then, of course, you can do B-swarm and violin all together. Okay. Anyway, so that was the visualization part. We'll get started with our actual data. So this actual data is taken from this website, which I'm going to encourage you to explore, because this course also involves doing a project. So this was taken from this website. Of course, there is health expenditure. A lot of this data, for example, is public. And this is a public health informatics course, so you should take a look at it. And next week, we'll discuss what kind of projects you will be working on. So here, I'm literally loading the data from GitHub. And first time you load anything, you should just see what does this look like. right? So it has a country, it has sex, it has region, year, and the BMI. Okay, very simple. Just 5 columns of worth of data. And what I'm interested in is this question, that is the BMI of men different from those of women. So just to keep the idea simple, I will only take the rural population here. So here I'm creating a new data frame by filtering, by only retaining rows which have sex to be men, region is rural, and year is 2017. And I'm just pulling out their BMI and calculating and just creating a new data frame. You don't have to do it this way, but I would like to just keep things simple. So let me show you what this looks like. So this is the data frame that I'm creating, right? So if I'm interested only in men versus women, I've already reduced the data frame to be a big long data frame which has only 2 columns, sex and BMI. This is all only of the rural population. And then of course I can plot it, and this is the plot that also we saw in the presentation. So it's actually taken from a real data from the world right now. Okay, the first thing we are interested to do is we are interested in checking whether these are normally distributed. Any ideas whether this is normally distributed or not? Do you even need to do a test to see whether this is normal or not? Is this normal? So it's not normal, right? It doesn't follow the usual properties of normality because it has 2 peaks. And while you can see this in your old data, if you do this plot, I'm just plotting. It's very simple to do this in R. You just do QQ norm and pass it the particular column, and then this QQ line which draws this line, right? So there's a 2-stage process. One second, just to explain. If I just do QQ norm, it will just plot this line, but of course I want the context as well, so I add a line to explain what deviation should I see. So this plot actually is very truthful to the distribution that you see previously, because you can see that initially there is a lot of deviation that's happening from normal in the lower quantiles, which is also what this particular part of the women. So I'm plotting the women, I think. No, this is men. So this is basically showing that assuming all the particular properties, at this stretch, there is deviation that's starting to happen from normality. And once I'm somewhere in the middle, again, I see a deviation which probably captures this trend line that is going up. And finally, things start to again deviate overall, right? So overall, if you were to quantify this, it does feel that this is not normal, right? But we are still going to abuse this assumption that this approximately normal should be satisfied. Go ahead, run the test, and we'll see that what would be the scenario if this assumption was to be fully untrue in your assignment. You'll do a simulation study to see what happens if the normality assumption is not true. For women, it's slightly better. There is some quantification, and of course there are also tests for normality, which for this class I don't care about it, because anyway the assumption about t-test requiring data to be normally distributed is a very small assumption. It does not actually impact your results extremely. Okay, so how do you do a t-test? Very simple. At least in R, it's very simple. I just do a t.test, right? So if I run a t.test, it prints certain things. This is my t statistic. This is the degrees of freedom. You don't have to calculate anything. This is the p-value. Okay, and then it reports 95% confidence interval, which we haven't discussed yet. We'll come to it in a later class. So this p-value is 0.00734. What does that mean? What should we do with the null? Okay, we should reject it, right? The p-value is our usual threshold is 0.05, and it anyway is very small, so we will reject the null, which means that the null was the men and the women BMI is equal, which we reject. This is under the assumption that my alternate hypothesis is what? What is my alternate hypothesis? That they are not different, right? Now I'm going to make a claim that the men BMI is larger than the women BMI. How should I do this test? The alternate is now men BMI is larger than women BMI. Okay, it's a singleton test. No, this is an alternate. I'm not changing my null. My null is the same. My alternate is the men BMI is larger than the women BMI. How should I do this test? This is only for people who come to the class. I will not upload this thing and you'll see this directly in your assignment. How should I do that test? How? So I want to do this test. Oh, double the p-value, huh? Okay. Listen closely. I want to test my alternate is mu male is greater than mu female. It's not a trick question. I just want you to think. I want to do this in using R only. I don't want to do any other fancy business. One thing which is useful to do in any language is make is to first read what is the function really doing. I told you, but you should not never believe me, right? You should go back and read what is written, at least code wise. I think content wise you can believe me, but like code wise you should always go and test what is going on. Right? So t.test, it is a documentation. One of the things about R is like you cannot upload packages anywhere if they are not documented. They need to be extremely well documented. That's why the quality of R packages is way above what you see in Python packages. But anyway, that's a separate discussion. So here there are two inputs that it can take. It's a numeric vector of data values, X, it's Y, it's an optional numeric vector of data values. And then there is an argument for alternative, which I actually hid, which I didn't even talk about. Why? Why did I not talk about this alternative? This is the null, this is the alternative hypothesis. Yes, so default is two-sided, right? But I have now changed my alternative. So what should I change? What input should I give to my t-test? Everything is here. Okay, let's do that. So alternative is greater. Okay, what happened? P value is 0.99. Why? Why is it that? 0.99. What happened? Yeah. So this was your, very simply, this was your mu male, right? Or let me just draw. Okay. So essentially this is not mu, but this is like, this is your distribution of males and this is your distribution of females. When you plot the data set itself, right, you know that you can see this difference. But this hypothesis of alternate and null is something which you would have come up about before. You cannot cheat. Like, so somebody, for example, would have been that males in this state are longer than or are taller than females. Somebody already had this hypothesis in my mind. So in this case, it was me. I was like, males BMI should be higher than females, right? But when you plotted the data, you almost saw that actually it's the other way around, right? So if this is indeed the other way around, then I still have to do the test. So when I do the test, essentially what is happening is I'm now going to plot mu males minus females. And overall, this is more on the negative side, right? So most of the things are the t statistic that you get here is, sorry, the t statistic, yes, that negative. So this t statistic you get here is this. What I am telling it is the alternate that I wanted to test is this. Now comes the definition of p-value. The probability of seeing something as extreme as this quantity. Now that extreme is of course defined by what is your alternate. In this case your alternate is males is greater than females. So which direction should I go? To calculate the p-value, you calculate the area under the curve essentially, right? This is your t statistic. This is what you're getting. Doesn't matter where it is, but how do I define the p-value here? Is this, there are only two possibilities, this area or that area. Okay, this is not clear and that's why people are not saying. But why is that bigger? Why is it that side?
Because it's always assumed to be on that, but we have to 1 minus that to get the actual value.
No, so let's look at the t value here, right? So minus 2.6 is your t value that you got. That's close but not fully close, right? So how is the p value defined? The probability of seeing something as extreme as your t statistic. That extreme is defined based on your alternate. That alternate is what? Males is greater than females. So this extreme is defined by this direction, not the other direction. And because this is already on the left side of your 0, t you can assume to be more or less symmetric. Well, it is a symmetric distribution. It adds up this extra 0.5, and that's why this value is very, very close. It's actually on the other extreme. So now if I change my hypothesis that female BMI is greater, or the male BMI is lower than females, then let's see what happens. Any ideas about what the p-value there would be? If I change this greater to be other way around, less, what should be the p-value? What should be the p-value? Decrease by, and can you predict what the p-value would be? Yeah, 1 minus what you saw earlier, right? Everyone sees why. Is this part clear? This needs to be very clear. If it is not clear, please come and talk to me, right? So this is 0.0038, 1 minus 0.9961. It is now the probability of seeing something as extreme, extreme being lower, so on this direction. Okay, so I'll not include this notebook or these kind of notes in the class because that's in the notes, because that's the point of coming to the class. Any questions? So please, if this is not clear, please clarify this before leaving. The null is remaining constant, right? The null has to be the simplest hypothesis you can think of. At each point you've already defined that the null is mu1 equal to mu2. The class is over. We will start with a new exercise in the next session. But if you have any questions, you can stay back. Yeah. So. Hmm. So when you define your null, right, your null remains fixed. Your alternate determines which direction should you focus on. So in this case, your mu1 is equal to mu2. That's the null that you began with. Your alternate, if you don't define anything, I assume that you don't care about which direction you're going. Then I refined it and I said that no, I want to test. Exactly. It has a side ingrained in it in that sense, because that comes from the alternate side. It's not directly ingrained in the null, right? You have to define what is your alternate. Because that's why this test does not know anything, right? The context comes from your side. What is that question that you are interested in? The male heights are longer, the taller, the women heights are taller. You can look for both sides, right? Because you're saying that they are very similar, so I don't care. But so I don't care which direction they go to. I don't care about it. All I care about is this same or not. For example, I don't care about whether. Right. it is condition. So that's why it says that if the null is true, what is the probability of seeing something as extreme as you did, which is actually determined by what your alternate is, which it doesn't explicitly spell out in the definition. Yeah, but it is dependent on what your alternate is. Okay, thank you.